Welcome on in. So in this video we're going to take a look at how antiderivatives can be used to evaluate something called a definite integral and how that can give us the area between a curve and the horizontal axis. So in physics we have already learned that if I take the area underneath a velocity versus time graph, that area will give me the displacement over that interval. And if our velocity function is just a nice linear function, then we could find the area underneath that trapezoid using a nice little geometric formula for the area underneath the trapezoid, right? But this is not possible if our function is some sort of curve. So next most complicated velocity versus time graph we could get is some sort of parabolic shape, right? We can estimate the area under that curve by doing multiple trapezoids or multiple rectangles. But if we use the antiderivative and the definite integral, we can actually find the exact numerical area between that curve and the horizontal axis to give us the exact displacement over that interval. All right? And remember, if we talk about acceleration versus time graphs, then the area between those graphs and the horizontal axis will give us the average velocity. All right? So how do we go about taking the definite integral? I will show you. So let's say we've got a function here for the position as a function of time equal to, let's go 3t squared. Start with something simple. All right? And let's say that we want to know, oh no, sorry, we can't have a position function here. We need to have a velocity function if we're going to talk about the the area being the displacement here. Okay, so let's say that we want to know what is the displacement from t equals 1 to t equals 3. Yeah? All right, so the first step in this is taking the antiderivative. All right, so the antiderivative of v is going to equal, remember this exponent goes up by 1, so we have t cubed, and then we divide the coefficient out front by the new exponent, and that is our antiderivative. Let's go ahead and add on the c here. So we end up with just t cubed plus c, yes? All right, so now comes the part. I'm going to show you how to do it. I'm not going to tell you why it works. All right? So really what we are doing is we are evaluating our definite integral from t equals 1 to t equals 3. So we're going to put our what's called our limits of integration right here from 1 to 3. Okay? Which means that we're going to evaluate this antiderivative from the upper limit first, and then we're going to subtract off the antiderivative evaluated at the lower limit. And that's going to give us the area underneath the curve. Okay, so upper limit goes first. So we're going to say, and let me just introduce some notation here. This is what I've tended to use in class. T cubed plus c evaluated at these limits. T equals 1 and t equals 3. Okay, so again, upper limit goes first. Upper limit gets plugged into t. All right, so we're going to have 3 cubed plus c. Let's not forget that. Then we're going to throw in a minus sign, and then we're going to evaluate at the lower limit. So we have 1 cubed plus c. All right, this is the integral of integral of v from 1 to 3. All right, and what we're going to see when we do this as well is another thing at the end of it, a dt there. And again, I'm not going to tell you why. I'm just going to tell you that this dt here, for our intents and purposes, tells us what variable we're integrating with respect to. All right, just like in a derivative, when we say dv dt, the dt part on the bottom says we're taking the derivative with respect to the variable t. If there's other variables in there, then I'm going to ignore them, consider them constants, and we're just doing that. So for the time being, don't stress out about this guy right here. Just understand that it's there to tell us what we're integrating with respect to. Okay? So the integral of v from 1 to 3 is going to be this guy right here. So let's go ahead. 3 cubed is 27, so 27 plus c, and we're going to go minus 1 plus c. All right? And remember the c was in there because there could have been a constant from taking the derivative that went away. So when we take the antiderivative, we end up with some potential constant. But look what happens to the constant here. We got 27 plus c minus 1 minus c. The c's cancel out. And that's going to happen every single time you take a definite integral, okay? Because you're always subtracting the lower limits evaluation from the upper limits evaluation. So that constant of integration, gone, always. And from here on out, I'm not even going to put it in when I take my antiderivative and I'm doing a definite integral. Okay? It's important to know that that is only true when you're taking a definite integral. If you see those limits of integration on your integral sign, you know you're taking a definite integral. If you don't see those limits of integration, then you're just taking an indefinite integral and the c has to stay there. Okay? So we end up here with 27 minus 1, 26, I think, I hope. If this actually is a displacement, it's going to be in meters, which means that this object moved 26 meters to the right of where it was at 1 second. So in 2 seconds, it travels 26 meters to the right. All right, so the definite integral will give us the area underneath any curve. Okay, and you have to remember, it's antiderivative first, and then you evaluate at the upper limit, throw in the minus sign, and evaluate at the lower limit. And then you got to do some arithmetic. Okay, and it gives us the exact area between any curve and the axis. Okay, let's see what happens if we've got area below the axis. Okay, so let's say we've got some interesting acceleration function here, t squared, negative t squared minus 2. It's a parabola opening downward. And let's say we want to know what is the change in velocity of this object from 0 to 1 second. So this is t equals 1. We know we're looking at the area between the curve and the axis. And we've memorized at this point that areas below the axis are negative. Let's see what happens when we take the definite integral here. So the first step is we are integrating from 0 seconds to 1 second. Those are again called the limits of integration. We're going to throw in the equation, negative t squared minus 2. And I'm going to slap on a dt at the end because I'm integrating with respect to t. Again, don't stress out about that. It just tells you what you're integrating with respect to. All right? So first step, take the antiderivative, add 1 to the exponent. So now we've got t cubed, and we need to divide by the new exponent, so negative 1/3. And then remember that 2, there's a t to the 0 right there. So add 1 to the 0, you get 1. Divide 2 by 1, you get 2. So we still have minus 2t. I'm not going to put on the c this time because I know it goes away when I do a definite integral. So here my notation is I'm evaluating this definite integral between those limits. Okay, so remember again, you plug in the upper limit first. All right, so it's negative 1/3 times 1 cubed minus 2 times 1. Okay, that's the upper limit. Slap on a negative. And then the lower limit, let's see, 0 cubed is 0, and 2 times 0 is 0, so we get 0 for the lower limit. And so we've got negative 1/3 minus 2, which gives us, let's see, that's 6/3, negative 7/3. Gosh, I hope I did that right. I always screw up my arithmetic. Negative 7/3. So we learned that area under a curve is negative, and in this case, indeed it is. So that is the actual numerical value of the area between that blue curve and the x-axis. And it's below the axis, so it is negative. What does it mean in a physics sense? That means that this object, its speed changed by negative 7/3 of a meter per second in that 1 second. All right? So however fast it was going at 0 seconds, which we actually don't know. I can't tell you how fast it's going at 1 second because I don't know how fast it was going at 0 seconds. I just know that its velocity changed by negative 7/3 in between 0 and 1. So we would need a little extra piece of information there, like the velocity at time 0 was 5. Then we go 5 minus 7/3. That would give us the velocity at 1 second right there. But remember that the area underneath this graph just gives us the change in velocity. Okay? So those are the nuts and bolts of definite integral. All right? Antiderivative, evaluate at the upper limit, subtract, evaluate at the lower limit. That's it for now.